It is my pleasure to announce today's speaker Vitalii Konarovskyi with the talk on stochastic partial differential equation, milled field limits, and stochastic gradient descent. All these interesting things. Okay, Vitalii, let's go.
Okay, thank you so much for the possibility to give a talk. My talk is based on the joint work with Benjamin Guess from Bielefeld University and Rishab Gavalani from the Max Planck Institute in Leipzig. And it is the continuation of my previous talk given here in April, where I derived a stochastic partial differential equation, which can be used for the analyzing of a stochastic gradient descent in the case of a huge number of parameters, or in other words, in the case of over-parameterization. We also discussed the well-positiveness of this equation. And today I want to compare solutions to this equation to the stochastic gradient descent and show that it gives better approximation than solutions to the corresponding deterministic partial differential equation known in the literature and which is used for the approximation or for the studying of stochastic gradient descent. And in order to make my talk self-contained, I would like to quickly repeat the derivation of the stochastic partial differential equation considered here and formulate the well-positiveness result. And after that, we will go to the comparison of solutions to that SPDE and the stochastic gradient descent. So therefore, I will need to repeat a few things which we discussed last time, just to make my talk clear for everyone. And let's mention that the stochastic gradient descent is and derives the main equation which appears for the description of the mean field scaling limit of the stochastic gradient descent. In my talk, we will focus on the classical settings of supervised learning. And let's assume we have a large training data set with inputs theta and labels gamma, which are assumed to be independent and identically distributed from an unknown distribution. For instance, theta I is an image of a cat or dog, and gamma I is 1 if a cat is on the picture or 0 otherwise. And our objective is to model the dependence of the labels gamma on the future input theta. In other words, we need to find a map F which map the inputs into labels. In our particular example about cats and dogs, the function F has to tell us who is on the picture, cat or dog. In the supervised learning, one can approximate the function f by functions fn of such a form, where xk are parameters which have to be found. For example, if the function u here has such a form, then in this case, we talk about the approximation of f by a network with one hidden layer. By the way, let's note that the number of parameters here can be very large. Ideally, the parameters x should be chosen as to minimize the risk generalization error L, where the small l is the certain loss function. And we will work with the square loss. Thus, the generalization error L measures the average of the square of the distance between the true value of the function and the approximation function. And here M is the distribution of inputs theta. The parameters xk can be learned by stochastic gradient descent, where every next iteration is the present iteration minus the gradient of the loss function computed at the true value of function f and the network, and also multiplied by the learning rate, which is a small parameter. So since we work with the square loss function, then the gradient of L has such a form. Okay. And then using the form of the function fn from the previous slide here, so you can see just computing that the difference and multiplying by the gradient of function u, we can see that this term is the gradient of the function fi, which is a multiplication of these two functions, and minus 1 over n and such a sum. And by the way, this sum here, it is just the integration of the function of the gradient of function k with respect to the empirical measure. And now, for simplicity of notations, let's denote that term here by the function. Okay, so the analyzing of machine learning algorithms is confronted with algorithms with a large number of parameters. And this motivates the analysis of scaling limit corresponding to the asymptotic regimes in which the number of parameters becomes large. And a remarkable feature of neural network is the observation that while they may be dramatically overparameterized, this doesn't lead to performance degradation. Roughly speaking, the landscape remains essentially unchanged as the number of parameters n goes to infinity. And at the moment, understanding of this phenomena is one of the important problems. So in this work, Song Mei with the co-authors showed that the empirical distribution mu n of the network parameters of following the stochastic gradient descent converges to the solution of such deterministic gradient flow equation. So where the function v here, it is the expectation of the function vi from the previous slide, and with such rate of convergence. So therefore, the mean field, the mean behavior of stochastic gradient descent can be analyzed by considering the limit.
Vitaly, can I ask you about the first formula with this 2 O large or capital? What does it mean exactly? Does it mean that we can have arbitrary convergence to the n to the infinity and delta t to 0, or they must be connected in some way? What does it mean, this formula?
Roughly speaking, it means the following one, that the distance, and if I remember correctly, in this work they talk about Wasserstein distance between the two, between the distributions of the process of the empirical process for the parameters of HGD and the solution to the flow equation. So behaves like that. It means the following: if you send that n to infinity and delta t to 0, you will see such kind of behavior.
In which way? Actually, my question was: do they must be connected when we make this limit, or they can go to infinity and to 0 in arbitrary way?
Yes, yes, of course. So this describes in any way. In particular, if you just say that this goes to zero slower and n goes to infinity fast, then you will see the behavior of that parameter.
Because it seems that the first command is very natural. It is just estimation of the distance between empirical measure and the distribution. So it is natural, and other one is more interesting. Why we have square?
I think that it is also very natural because it actually captures how you discretize the continuous picture.
Yes, but we have a deterministic equation, and then one can expect, as usual, that when we have some conversion, it must be like delta key, not like square root. You see, some
square root t, it is the worst. I'm not talking about here about the optimal.
Oh, I see. Okay. Okay, I see.
Okay. Good, but I just would like to note here that you see, if we take here t delta t going to 0 like 1 over n, then we have the rate of convergence like 1 divided by square root n. And we will come back to that later in my talk. Okay, good. So the problem here is that the passing to the process mu, just for the for studying of the stochastic gradient descent, all of the information about the fluctuations of the stochastic gradient descent is lost. But there is an empirical evidence that stochasticity is very important for the implicit bias of stochastic gradient descent. For instance, it helps to avoid all local minima of generalization error. So therefore, universal limiting models incorporating those fluctuations are needed. And in my talk, I'm going to identify a class of nonlinear conservative stochastic partial differential equations which serve as such a fluctuating continuum model, and show that this equation which we obtain gives a better approximation of the stochastic gradient dynamics than the deterministic stochastic differential equation from this slide. And in order to get such an stochastic partial differential equation, we need to come back to the stochastic gradient descent, and so it is here, and then we need to add and subtract the expectation of Vi, and you can see that this equality here, it is just the Euler scheme for such system of stochastic differential equations driven by correlated Brownian motions. With the correlation between the Brownian motion Wk and Wu equals the covariance of the covariance matrix, which depends on xk, xl, and the empirical measure, because the function v depends on on parameters and the empirical measure. And hence we came to the following, to this system of stochastic differential equation, where mu n here is the empirical measure, and A tilde has a covariance structure, and in particular, every entry of A tilde can be written as the expectation of some function g, which depends on the position x and the measure mu. And then, in order to get the equation, we need, for the empirical measure, we need to take the test function, and then using the Ito formula, we can see that the integral of the test function phi with respect to empirical measure satisfies such an equal. So this, where A here, it is just this A tilde computed at the same point, Sx. and this the martingale part here, which has such a covariance structure.
And what is alpha?
And alpha, it is the learning rate. So it is here. So I need to go back and show that it was square root delta t, but this is not very good for the notation, always to write delta t. So therefore, I would like to write square root alpha instead of delta t. Okay. And then assuming that the number n of parameters x converges to infinity, and the initial parameters xi are independent, identically distributed with a distribution mu0, we can see that the empirical process of the parameters should converge to a solution to such a martingale problem. Where here as A is
Vitaly, why you are speaking only about the martingale problem? Why you don't speak about the equationless interaction, which you can get also from this? You can consider also together with this one.
Here I try to follow this work which will appear, which has to appear soon in Communications on Pure and Applied Mathematics, where this equation was derived. And actually, at that moment, when we started to work with that equation, it was not clear that the equation with interaction can be written. So the idea of
if you can you go back for one slide, please, where you just give the this characteristic of the martingale, yeah. Why not to say that it depends on the empirical measure? And we can just have, for example, Wiener sheet, and then integrate with respect to it.
No, look, let's consider only that part.
Yes,
if you
exactly.
consider only this part and assume that which comes very natural, I mean, from
yes.
part,
Mm-hmm.
And therefore, you cannot say nothing about the Brownian sheet and so on, because here you need to put inside the problem or so some additional information about the noise. So therefore,
you already introduced Brownian motion without any problem. Why not to introduce here again Brownian sheet where you can get all this BK integrating some kernel with respect to this.
Okay, if you can, right, and if you can see that, then everything becomes very obvious. And I'm going to say about that in the next slide.
Oh, okay.
Of course, I mean, when we started to work on that equation, our idea was everything what we had and what was in that paper. It is indeed a very big paper where they introduced that equation and then try to analyze that equation, but it is machine learning paper without strong mathematical proofs and so on. So therefore, when we saw that equation, we saw, okay, so we have like that martingale problem. What should we do? And the first step, which would be probably natural, to assume that we have the stochastic partial differential equation with the square root of that coefficient. But then you would come to the singular stochastic partial differential equation. And then the second idea was that indeed, let's assume that the noise has a special structure, exactly as you said. So, and after that, assuming that we work not with the martingale problem, but with the solution to the stochastic partial differential equation, with this, exactly with that noise, we can it is random. I mean,
now it is random. Yeah.
Yes. And the problem here, why you get random object, because you don't have so much, probably it is my vision, that you don't have so much independence into between particles to have something like the
Classical
limit or propagation by House and so on. You have here a lot of really dependence, so therefore at the limit you should see something which is random. Okay, so and by the way, if you assume that the noise, that the martingale part has that form, that the simple computation gives you exactly what we had before. So therefore, we want to work with such an equation, which we will call the stochastic mean field equation. So it was our name. We spent some time just to propose some name, and we stopped on that. Okay, then let's call this equation stochastic mean field equation, and this equation I want to show today that it can be used for as a good approximation for the stochastic gradient descent in the case when the number of parameters is large. Okay. And in my previous talk was devoted to the well-postedness of the superposition principle of that stochastic mean field equation. And let's very briefly give the definition of a solution to that equation. We say that mu t is a solution to the stochastic mean field equation if for any test function this relationship holds. I mean, very standard for the solution of SPDEs. And also last time, to define a solution to the stochastic mean field equation, we considered the stochastic differential equation with interaction, which first appeared in works of Kotelenets and Andrei Anatolyevich Dorogovtsev. And this equation describes the dynamics for particles started from every point, and the motion of every particle depends also on the mass which is transported by this particle system. And if we assume that the coefficients are Lipschitz continuous with respect to both variables, then for every initial condition, which is a probability measure with the second moment, the solution to that equation has a unique solution. And also last time we said that if the coefficients to that equations are Lipschitz continuous with respect to both variables, and smooth enough with respect to the special variable. Here, I don't want to write the precise conditions. I did that last time. I just remind you. Then we know that mu t, that this equation has a unique solution, which has such a form. I mean, the solution can be written as that, or the solution to that equation, to this equation, describes the evolution of particles which are transported by the family of processes defined by this stochastic differential equation with interaction. And we called such a solution a superposition solution. And this fact allows us to study the limiting behavior of solution to the stochastic mean field equation. And since we will work with the Wasserstein distance, let's briefly remind the definition of the Wasserstein distance on the space of probability measures on a Polish space with a finite p moment. So the p Wasserstein distance between two measures, ρ1 and ρ2, it is the infimum of such an integrals where the infimum is taken over all probability measures with marginals ρ1 and ρ2. And usually, I mean, using the probabilistic interpretation, it is the infimum of such expectations over all couplings psi1 and psi2 with distributions ρ1 and ρ2 respectively. And we know also that the space of probability measures equipped with the Wasserstein distance is a Polish space. And we start the discussion of the limiting behavior of solutions to the stochastic mean field equation from the convergence of the empirical measures. So let mu and mu alpha be superposition solutions to such an equation started from the empirical distribution and from measure mu0 respectively. So here I remind that xi are independent, identically distributed with distribution mu0 random variables. By the way, let's note that this process here is the empirical distribution for the family of n parameters of our from our motivation part. And we have shown that this process converges to the process mu alpha with such a rate of convergence where the constants here are independent of alpha, of the learning rate.
And mu t now is mu alpha. So it is just notation. You have equation d mu t, so this is mu alpha. Or
d mu yes, of course. I just wanted to write one equation for both equation for both processes. Here, both processes satisfy this equation, but they just started from different.
I see.
Vitaly, let me ask you the following. Do you have, because you already have a solution, a theorem of existence, the uniqueness of the solution under Lipschitz conditions, maybe you have the estimation on the distance between two measure-valued solutions starting from two different measures. Do you have such estimation?
Yes, of course. I didn't want to make my talk very complicated. And since
then it seems that if you have such estimation, then what actually you are saying here, that you can measure the empirical, distance between empirical measure and the distribution, and it is expectable that it is n-1, yeah?
Yes, of course.
Maybe you even can have another term, or it will be interesting to have another term, like central limit theorem.
I will tell about that.
For processes.
Yes, but let's do everything step by step.
Okay.
So I just since I have some time and I have some number of slides, I should be in time. So therefore, I will not skip something. Let me just follow as I decided to do, preparing this talk. And just for the full picture, I mean, the proof of this fact is very similar to the proof of the continuous dependence of the solution to the stochastic differential equation with interaction introduced by, for example, by Andrei Anatolyevich Dorogovtsev, driven by a Brownian sheet. So here only the difference is that you don't work with Brownian sheet, but you work with the cylindrical Brownian motion. But actually the proofs of this inequality is the same, and it's based on the fact that we work with superposition solution, that we can go from the equation from the stochastic mean field equation to the equation of such a form. So I mean, these processes you can they have flow structure where this where here x satisfies that equation, and then everything what we need to do, we need to consider the difference between two different solutions starting from different initial positions u and v. Then using the Lipschitz continuity, you can control the supremum by the initial condition, and then by the difference of that term, and then by Lipschitz continuity, you will have here the supremum of the difference, like here, and then plus the expectation of the Wasserstein distance square between two measures transported by that flow. And therefore, using the Grenoble inequality, you can control that measure these marginals mu0 and mu0. You can see that the expectation of the supremum of the Wasserstein distance square can be controlled by such an integral, between here is the difference between between solutions starting from different points u and v with respect to this measure which you fixed. And then using the previous estimate, you can control this via the difference of initial conditions and also the expectation of the Wasserstein distance. And after that, you need to take the infimum over all mu with z marginals. You will get the Wasserstein distance here, and you can also, of course, here put supremum. And after that, use the Grunewald inequality. Therefore, you can control this via the initial distribution, via the initial condition. And then, by the way, what is very expectable, as said Andrei Anatolyevich, that actually we can control the distance between Wasserstein distance between two initial distributions, like 1 over. I mean, and we have the rate of convergence 1 over. So, for instance, I can refer you to that. Also, applying the similar approach, we can get the rate of convergence of solutions to the stochastic mean field equation to the non-fluctuating solutions to this equation as the learning rate goes to 0. And we also can see that the expectation of supremum between of the Wasserstein distance squared between these two solutions can be controlled as alpha, or the distance can be controlled as square root alpha. And the proof is the same. Therefore, combining the two last statements, when n goes to infinity and alpha goes to 0, we can see that if alpha is equal to 1 over n, then the empirical distribution for n parameters converge to the solution of this equation with the rate of convergence 1 over n. So roughly speaking, you can write this, the empirical process as mu0 plus capital O of n to the power of -1 over 2. And after obtaining this result, we would like to we study the fluctuations of this process around mu t0, like in the central limits here. So therefore, for this, we considered the difference between two solutions and also normalized them by that constant. And also we assumed we made some additional assumptions on the coefficients. First of all, when we go back to the motivation part, you can see that this function v in the equation, in the drift term of the equation, has a linear structure. It is some function v plus the integral of some kernel with respect to measure mu. And also we assumed that coefficients are smooth enough. So in particular, so this function, here this is that the usual supremum norm in the space of g times continuously differentiable function, and this is a mixed norm. Like supremum norm is in the space CG, C iota, and the Sobolev space. Okay, and then we showed that the fluctuations around the mean field limit converges to the Gaussian unique solution to such a linear stochastic partial differential equation, and also we can control the Sobolev norm of the convergence. And we show that it is also like 1 over, the expectation of the Sobolev norm square goes to 0, like 1 over
Vitalik, and eta n are measures.
Yes.
And eta n for fixed t, eta and for fixed t and omega, it is discrete measure, correct?
Mm-hmm.
And you consider
because it is different.
Yes,
it is
yes.
not only
I see.
It's,
And
general measure.
Yes,
yeah,
it is
side
also
measures.
kind measure.
Yes, and so this convergence is in some generalized sense. You
Yes,
have
it is
index
the
minus
W
J.
norm. And this, I didn't
Yes,
put that.
but what is strange that, for example, suppose we have no any equation, we just have empirical empirical measure and limiting measure mu zero, and take such a difference, normalize it, we will have only weak convergence, not.
No, look.
Why not?
I mean, first of all, we are working on the same probability space.
And what?
You say we have weak convergence. You mean
for
like
example,
measures or
what about
probability?
any coefficients? Just say that all coefficients are equal to zero. Then mu zero remains to be mu zero, and mu n remains to be mu n. Yes, it does not depend on t. Mu n is just empirical measure. You base it on the sampling x1 and xn. Then what we have usually, we have weak convergence, yeah, to Gaussian distribution.
Unfortunately, we could not get the conversions. We got the conversion in that negative Sobolev space.
But weak convergence relatively to probability argument, I mean, in sense of distribution, because the central limit theorem is the distributional theorem, yeah?
Okay. It is, I got what you mean here.
Exactly, yes. Here is the conclusion. Looks very strange, yeah?
It is right, because actually our formulation is for fixed when our initial distribution is I mean, we can control this difference via the difference between the initial distribution. And in our work, we assumed that we work with just non-random initial conditions.
Okay, but mu n is random, yes?
So therefore, mu n is random. Therefore, here you have two sources of randomness. One which comes from the initial condition,
yes, and
another
another
which
one
comes
from
from the noise.
Yes, forget about noise. Suppose that all coefficients are equal to zero. You have just empirical distribution.
No. Andrei Anatolyevich, I need to be here more careful in the formulation. Okay, I agree, and formulation here should be the following: that conditioning on the initial distribution, you have such kind of convergence.
What does it mean, conditioning? That you have fixed sample sequence.
When we fix one randomness, right? So therefore, it will converge to zero with such a rate of convergence if this randomness also goes to zero with such rate of convergence. So
this is like you have there are a lot of such results. Maybe Bobkov was one of the first who began to consider this two randomness stuff for plus minus one in the central limit theorem. He just add randomly signs to summands and then fixed the signs. So if we fix it one, by the way, it can be interesting for you because there are interesting estimations there, maybe related.
And by the way, another formulation here also could be the following: that first of all, you just consider the empirical distribution, which converge in weak sense to the initial distribution.
Exactly.
Then you put them on the same probability space. You will have the convergence almost surely. And after that, you can formulate that result, just putting all initial distributions on the same probability space.
Still, it looks slightly strange. I mean, because you see, it's strange. Can you just explain again what do you mean there? What is eta n now? Because this formula definitely is not good. Yeah. Yeah. So we have to reformulate the conclusion or to do something here.
Okay. Let me do that because I think that I connected my tablet. I just share the screen. Okay. And then the screen and make more formulation. Stop sharing. Good. So you can see my screen. And here the formulation should be the following: that let's assume that we have mu n of t, which is obtained like mu square root n of mu say 1 over of n, like before, minus mu.
With t, indexed by t, yeah?
Of course.
Andrei Anatolyevich, do I understand correct that you ask about, assume that you have zero diffusion and zero
drip.
Zero. So you may even skip this t.
Exactly. Yeah.
So
then we have only
Vitalii, yes. Assume that the coefficients are zero, then you have just
yes.
Explain us what happens with initial conditions.
Exactly. Yeah.
So our point here was the following: that I mean, because I tried to just make the statement, I mean here, which is which pass to my motivation, and here let's assume that we have some parameter, okay, it is n, and here is mu t, where mu t n, it is just, if you like, any process, not necessarily empirical process, but we started from from mu 0 n, and also you have mu t, the process which started from mu 0. They are non-random. Then after that, also let's assume that mu 0
who are non-random?
This.
But in your formulation, they are random. From this randomness, you get Gaussianity of the limit.
Not from that.
Exactly.
Not,
this is a source of Gaussianity.
Not only because we have linear equation, we also have another source of randomness.
Yes, you have another source of randomness, but those randomness do not give you Gaussianity. As I said, forgot about coefficients. Suppose that they are equal 0. All they equal to 0. All
yes, of course.
Then you have just Gaussian limit, but weak limit.
Yes, of course.
Like Brownian bridge in Kolmogorov-Smirnov criteria.
So let me first of all formulate the statement which I want to show you the idea of proof, and which I want to,
I don't understand the statement which you want to prove. You see, so
Vitalik, and what about initial condition? Is it dominated by 1 over n distance between?
So let me finish the formulation of the statement. So I said that let's consider mu Tn, which is a solution to the stochastic mean field equation, started from some initial condition, mu 0 n. So
deterministic.
It is deterministic, right?
Okay.
It is not random. Then let's assume that mu t is also so started also a solution to the stochastic mean field equation without noise, and we started with that thing. Okay. Then after that, and by the way, and here your alpha for that equation, your alpha is equal to 1 over n, and here your alpha is equal to 0. This alpha is the coefficient near the noise.
Yeah.
Okay. Then let's also assume that mu n square root n minus mu 0 n minus mu 0 converge to some atom 0
In which sense?
in the Sobolev space H minus J
Okay.
with rate, right, 1 square root n.
Okay, why not?
Then I claim that eta Tn minus eta T, which is well defined now, I can put here supremum, it is the norm of minus.
What is eta? You don't need maybe.
So it is, oh, I'm sorry.
What is?
Yes, of course. Eta T, it is square root n mu T n minus mu T.
Yes. You already have this formula
Yes.
in the top of the
Of course, and this converge, I mean, when you consider, and also eta T is a solution to the linear SPDE on the slide started from eta 0.
From eta 0.
Right. Also deterministic, because this is deterministic. And
Okay. It's believable.
Then the difference can be controlled like that. So it is exactly statement which we proved.
Okay. So it has nothing with empirical distributions, yeah?
It has nothing with empirical distributions, right? Yes and no. Because you can apply this statement to the empirical distribution. And here the idea is the following. So let's take an independent random variables xi or this empirical distribution. I will write in different color. Mu 0 n delta xk, and which are empirical and which converge to mu 0. And then let's put them all on the same probability space, where you will have the convergence almost surely.
Maybe you don't need to do this in this stage, because now you have the good convergence. They converge almost surely without any new probability space. This one goes almost surely.
Okay, very good. So then when we have this one, then you can start from these initial conditions, the solution to the stochastic mean field equation.
Yes.
All right, and then you can consider, like also the solution which started from there.
Yes.
And then our statement. By the way, I didn't here said that because since I wanted to talk about the empirical and I wanted to put the constant here, I just want to add here that this convergence, when you put here the supremum between eta and t minus eta t, and take the expectation, it is less or equal than this 1 over n, which is exactly here square, which is that noise, and also plus the difference between the initial condition.
Exactly.
So square here. Right, and here is the expectation. So therefore, I mean, when you want to talk about the empirical distribution, what you need to do, you first of all the fixed randomness, this randomness here, right? And you can apply that statement. So taking the expectation with respect to randomness generated by Brownian motion, you have that one. Right?
Yes.
And after that, you take one more expectation. So therefore, you will have here like the double expectation.
Still, it is not clear. You have this empirical distribution. Then what will be eta, and in which sense you have convergence? Let us check it.
Okay, you want to say that I skip n converge to this in weak sense.
Yes.
Let's use plus Konarovskyi. You have strong sense.
we will have
Right.
a strong sense, but we lose the structure
No,
of
and
empirical
after
measures.
that, after we use the structure of empirical measure. Why? You can take mu and
Because when you reorganize the space in order to have convergence of these empirical measures, you lose that they are empirical measures obtained from sampling. You can lose it, yeah. Of xk, but series of xk. For every n, you will have another series of independent random variable which you get from which you get this empirical distribution. But it seems to me that this is a matter of the discussion, a technical discussion, and let's skip it. Let's skip it for a moment and go further.
Right part, right?
We
can talk about it.
Yes, this seems to be right. So let's go to the next step of your talk, because we have a limit in the time. Yeah.
Of course, but the reason is also I wanted to show how we obtain that result. Let me stop the sharing here, and also I need to switch. So I can do that. And then I will. Okay, my idea here was to show you that how we can also prove that that fact, but probably now I will skip that because as I understand this result was expectable.
Yes, we can go further.
But also the problem is that my talk somehow is based exactly on that empirical, I mean, with that trick, with the empirical distribution. So let's try to see, probably I should finish on the formulation of this result, or probably I will go further. So, because actually, let me tell you about idea. So I wanted to complete my talk with the following observation that roughly speaking, we know now that the empirical distribution has such an expression, right? Where at least we have the big convergence. We have where you agree that when eta n goes to eta, at least in the big sense. Okay, there was some question about the control of the norm and so on, where we had the problem with the initial distribution. But at least formally we have that expansion.
Of course, yes. Eta t.
Vitalii, eta t. It is a process.
Of course, yes, of course. I apologize for that. For every t, you have that expression, and also it is known from the paper of these mathematicians from 2020 that the stochastic gradient descent also has such kind of expression. So with the same eta here, so eta satisfies the same equation. Therefore, at least formally, when you consider the difference, you should see something like capital like small o by small o, because here it is not known the precise asymptotic. So here you have exactly the convergence. You have exactly the convergence with. You have the convergence, V convergence. So therefore, you need to be able to talk about the rate of convergence. You need to use something like Stein method and so on. So at the moment, it is unknown whether you have also such kind of asymptotics like here. And by the way, in order to correct myself also, we can here assume that, say, we start from, say from that, no. let's go ahead. And then our last result, which I would like to show you, is that actually we can realize that that in the region of space. So we can show that considering the difference, the Wasserstein difference between the distributions of the empirical process described by the stochastic mean field equation and the distribution, path distribution of the stochastic gradient descent has asymptotic better than 1 over n to the 1 over square root of n. So, and the idea here was the following. I mean, when you want to talk about the Wasserstein distance, I mean, let's consider the Wasserstein distance between two measures multiplied by square root. Then we know that the Wasserstein distance is infimum. I can put here infimum, and then I can do the following trick. First of all, I can put inside the same initial, I mean, non-random. Solution to the deterministic equation, and then I can put also square root m inside the expectation. So therefore, here you can see the difference of eta, and then you see so the Wasserstein distance between two etas, and then using the triangle inequality, you can put you can put the law of the process f, for which you have the right rate of conversion. So therefore, we can see that this goes to 0 because that converges to that, and that also converges to that. So therefore, actually, you get that this empirical distribution goes to this. So this the order larger than 1 divided by square root of. Okay, and just to complete my talk, so I just would like to make the following conclusion, that from the result above, we see that the stochastic mean field equation provides a higher order approximation to the stochastic gradient descent than the approximation by the non-fluctuating limit mu0, and which gives the order only 1 over square root n. As we know from the motivation part, and it is due to the fact that the stochastic gradient descent and also that the fluctuations in that stochastic mean field dynamics have actually the same fluctuation in the central limits here. And the precise, more details you can find in this work, which is on archive. And thank you for your attention.
Okay, thank you very much. And what I have to say is that this work has some possibility of refinement because there are a lot of good papers related to convergence of empirical distributions to initial distributions, and maybe one of the experts is Vladimir Kolchinsky. Who works in Kansas University, and Évariste Genet. These two persons did a lot in this direction, especially in different conversions. Also, of course, Vapnik-Chervonenkis with a different approach also did a lot in the refinement of the central limit theorem for empirical distributions. Okay, thank you. And maybe some other questions or comments, please.
I have only one question, because I don't understand why the difference between initial conditions disappear. Okay, let us assume that we used Skorokhod theorem on a joint probability space and assume that you have convergence of square root of n times empirical distribution minus mu to some Gaussian measure. But expectation of the difference between in this central limit theorem does not appear in the result. And actually,
Vitalii wrote some formula by I thought by the green light. He wrote this plus
Plus
different
initial
initial.
condition, right?
yes, but then it disappears, and I'm not sure that this convergence is better than square root of n, 1 over square root of n.
I mean, in the central limit theorem, you also have, because you have Stein method, right? And also you can see that it is like the asymptotics like 1 over square root n. But when you just consider the difference between laws, the difference between laws, it will go also like 1 divided by square root n.
And how do you prove this? So because your space are very specific. So
No, I mean, when you talk about the initial conditions, they are just measures on the space of, I mean, on RD, say, and your eta is a Gaussian random variable, right? So therefore, using Stein method, you can also talk about how fast something goes to the Gaussian limit.
Okay, this is about those main theorems, so it must be reformulated, of course. Yeah.
Of course, you will do that more carefully.
Okay, so thank you again. And Georgi, who will be the next speaker?
Nikolai Vovchansky.
Okay. So thanks everybody and see you next week. Bye.
Thank you. Bye.
Thank you. Bye.
Thank you. Bye.
Have a good day.
Bye.